You know, some of the most critical software in our world, the stuff we really depend on, is designed to never, ever stop. We're talking about the code running a power grid or an airplane's autopilot, or even something as personal as a pacemaker. These systems have to run continuously, reacting to everything around them. But that brings up a really big question. And that's a huge challenge, right? I mean, if a program doesn't have an endpoint, how can you possibly test every outcome? You can't just hit run, wait for it to finish, and check the answer. Its whole job is to keep running, correctly, forever. And for these critical systems, what we call reactive systems, the stakes are just about as high as they get. We need total certainty. We need a way to mathematically prove that no matter what happens, the system is going to behave exactly like it's supposed to. This isn't just about squashing bugs. It's about proving their absence across an infinite timeline. So, how in the world did we solve this forever problem? Well, computer scientists turned to a field you probably wouldn't expect: philosophy. They needed a totally new kind of language, one built from the ground up just to talk about time. So, back in 1977, a computer scientist named Amir Punelli published this incredible, groundbreaking paper. He had a brilliant idea. What if we took temporal logic, this tool that logicians had been using for ages to reason about concepts like necessity and possibility, and just applied it directly to computer programs? And that, right there, was the breakthrough. Okay, so the most important thing to get here is that temporal logic, it isn't a programming language. You don't write code with it. It's a specification language. It gives us this really precise mathematical vocabulary to write down the rules a system has to follow. Rules about what must always be true, what has to happen eventually, and how the past shapes the future. All right, so let's peek under the hood. How does this language actually work? Well, to make these statements about time, temporal logic uses these special symbols called temporal operators. You can think of them as the basic building blocks, the Legos of this new language. We're going to look at the two most common ones. First up, we've got the always operator. Sometimes it's called henceforth, and you'll see it written as this little box symbol. When you stick this box in front of a statement, you're saying something powerful. You're saying that statement isn't just true right now, it's going to be true for all future moments, forever, with zero exceptions. And the classic example here is just perfect: an elevator. If we were writing the rules for a safe elevator, we'd write a rule like this: always, the doors are closed while the elevator is moving. It's not good enough for this to be true most of the time or almost all the time. For the system to be safe, it has to be true continuously. Okay, so our next key operator is called eventually, or sometimes finally, and it's represented by this diamond symbol. Now, this one makes a different kind of promise. It's a guarantee that a property will become true at some point. It doesn't say when, just that it's absolutely going to happen down the line. So back to our trusty elevator. A perfect rule using this operator would be, if you press a floor button, then eventually the elevator arrives at that floor. See the difference? We're not saying it gets there instantly. We're just guaranteeing that the system won't forget about your request. That promise will be kept. Now, once you start using these operators to talk about the future, you run into a really deep, almost philosophical question. Is there just one single inevitable future, or are there many possible futures? This question actually leads to two major flavors of temporal logic. And this is where things split into two big camps. On one side, you have linear time logic, or LTL, which thinks about a single future path. And on the other side, you have computation tree logic, or CTL, which considers a whole branching tree of all possible futures. So, you can think of LTL like this. It looks at one entire run of a program, like one straight road from beginning to way off in the future, and it asks, does this specific path follow the rules? So a statement in LTL like, eventually the system will reset, means that along this particular timeline, a reset is guaranteed to happen. CTL, though, sees time completely differently. It sees a whole tree of branching paths, all the choices and possibilities that could happen. So a typical CTL statement is more about potential. It might say something like, from right where we are now, is it possible to get to a reset state? It knows there are other paths where you might not reset, but it confirms that the option is always there. All right, so we've got this amazing language for writing down these super precise rules about time. But what do you do with it? How do you actually use this to check something real, like that pacemaker software? This is where all this theory turns into a seriously powerful engineering tool. And here's the real magic. We don't have to do the hard work ourselves. The whole point is to get a computer to do the heavy lifting for us. This automated verification process has a name. It's called model checking. The process basically works like this. First, engineers build a formal model of their system. Then they write out all the critical rules in temporal logic. Then they unleash an automated checker that just explores every single possibility. And the result is incredible. You either get a mathematical proof that your system is correct, or, and this is the amazing part, it gives you a perfect roadmap, a counterexample, that shows you exactly where and how things go wrong. So let's zoom out. What's the big takeaway from all this? Well, this whole shift from a person staring at code to an automated proof was a massive change in how we build technology we can rely on. Look, at the end of the day, temporal logic and model checking completely changed the game. They took verification from being this kind of manual art form and turned it into a real automated engineering discipline. It's the hidden foundation under so much of the reliable tech we all depend on every single day. And that leaves us with a huge question for today. Temporal logic was designed for systems that follow predictable rules. But now we're building these incredibly complex AI systems that learn and adapt on their own. How do we verify them? What new kinds of logic, what new languages will we have to invent to prove that an AI isn't just correct, but that it's also fair and ethical and ultimately trustworthy? That's the next great frontier.